So today we are going to evaluate and solve polynomial equations with complex numbers. So our learning targets are evaluate polynomial functions at a complex R number, solve a polynomial equation with complex coefficients. So we have two ways to evaluate. We can either use direct substitution or we can use synthetic division. So when they're doing f of a certain value, and we can either use one of those two tools in order to get us our solution there. So evaluate the following function. So this first one here, let's try using direct substitution. So if they ask us to find what is f of 1 plus 3i, we just go ahead and take 1 plus 3i and plug it in there for the x's. So let's do that. So notice I just put 1 plus 3i in for each of the x's. Now, the biggest mistake that people make here is they really want to just go ahead and distribute that 3 right here, this 3. They want to distribute that through the parentheses. That's not what that means. 1 plus 3i to the third means 1 plus 3i times 1 plus 3i times 1 plus 3i. And then the next one there, it's minus 3. People want to go ahead and distribute that minus 3 through the parenthesis that follows it right there. So they want to take this minus 3 and they want to distribute it into that following parentheses there, but you can't do that. You have to do the parentheses there. It says squared first. You have to square it first. You remember your PEMDAS? It goes parentheses, exponents, then multiplication, and division. So we have to do our exponent there first. And so that means 1 plus 3i times 1 plus 3i. All right, so let's go ahead and let's do that. I think I'm going to come over here on the side and do the math on this. So if I multiply that, so I think I'm going to go ahead and the one that I have over there in green over there, I'm going to do that first. I'm going to do 1 plus 3i times 1 plus 3i. So when I do that, I can just fold that out or take 1 and distribute through the second set of parentheses, then take 3i and distribute through the second set of parentheses. So doing so, we get knowing that that I squared over there has a value there of a negative 1. So negative 1 times 9, there's a minus 9. Now combine that 1 plus negative 9 there gives us a negative 8. So negative 8 plus 6i. We always try to keep it in the a plus bi form. So the integer there goes first, or that constant term goes first, and then the I term there goes second. So since we already found what 1 plus 3i times 1 plus 3i there is, in that place right there, I'm going to put a negative 8 plus 6i. And then we still have to multiply that, so let's do that. So we can fold that out. So negative 8 times 1, there is a negative 8. Negative 8 times 3i, there is a minus 24i. 6i times 1, there is 6i. 6i times 3i, there is 18i squared. Let's go ahead and combine our like terms. Oops. 18i. And then remember that I squared there has a value of a -1, so -1 times 18 over there is a -18. Combine your -8 and your -18, you get -26. All right, so coming back up here, we have f of 1 plus 3i is equal to, we just found out 1 plus 3i times 1 plus 3i times 1 plus 3i there is a -26 minus 18i. And then minus 3, and we found out 1 plus 3i times 1 plus 3i there is -8 plus 6i. All right, so now let's just go ahead and distribute that -3 through. And then we can just simply combine all our like terms. So we've got a -26, a +24, a 1, and a -3. So that gives us a -4. And then we've got a -18i, a -18i, and a +3. Gives us a -33i. That is our solution. That is using direct substitution. So now let me show you how to do one here using synthetic division. So you could choose to use this one instead. So they're saying find f of 1 minus I. So a way that we can figure that out there, if you're way we can figure that out there is that we can go ahead and put that inside the box. And then our coefficients over here using synthetic division here, we can put in the coefficients 1, and then we got a -2, but because we're doing, we're dividing this by, or using synthetic division over here with 1 minus I, the easiest way to do this here is to put a +0i with this, because it's just a constant there with it, so we need the other part as well. And then a -3, and I'm going to put a +0i there as well. So I'm going to draw a line there. I'm going to bring down my first term. I'm going to multiply by what's in the box, so I get a 1 minus I. Add them together, so you have to add -2 plus 1 there is a -1, and 0 plus a -I there is a -I. Then I have to take 1 minus I times a -1 minus I. And so I probably am going to have to come down here and do my math on this. So 1 times a -1, there's a -1. 1 times a minus I, there's a minus I. -I times a -1, there's a plus I. And a minus I times a minus I, there is a plus I squared. So the middle terms there cancel out. I squared there has a value of a -1. So I'm putting a -2 over there. Now I'm supposed to add those together. And I get a -5. So what happens here, this is what's called the remainder theorem. Whatever the remainder there ends up being our solution there. So whatever you're plugging in there, let's say you're plugging in P of 3, you'll get some kind of answer. If you go ahead and use the remainder theorem, says that you could plug that into the box there, have whatever kind of a polynomial you want, do your math there, and whatever your remainder there, that is your answer right there. So we did f of 1 minus I. What our remainder ended up being a negative 5, so f of 1 minus I there is negative 5. So you get to choose which way you want to do this. Do you want to use your synthetic division there, or do you want to go ahead and use direct substitution? I always think direct substitution is a lot easier when you don't have something being added or subtracted from the I term there. So I use direct substitution when it's just that. But you have to remember what that means. It means a negative 2i times a negative 2i. So that's 4i squared. Remember I squared there has a value of negative 1 there, so that becomes a negative 4. Combine your constants there. Negative 4 plus 7 there is a 3. So we just end up here with f of negative 2i. So whenever I just have a single, this is called a monomial here. A binomial would be two terms connected by addition or subtraction. When you just have a single term there, they're just connected by multiplication. That's when I always use direct substitution, but it's up to you. The other way we could have done that and so you could have done it this way as well. Negative 2i would have gone inside the box if you wanted to. You would have put a 1 there, then the constant that's in front of the x there, the coefficient there, which is a 4, and you put 4 plus 0i. And then you got your constant term over there, which is 7, so you put a 7 plus 0i over there. And then you could have done that, and then your remainder would have been your answer, which would have been 3 minus 8i. So our next one here is supposed to find f of 3 plus 2i. It's a binomial. It's two terms that are connected by addition or subtraction. So again, I like to use synthetic division when it's something like this. So that's the 0 there. We're going to plug that in there. So it becomes 1. Just be careful with this one because it really matters if you miss the zeros. So remember there's a 0x squared. So I need to put the 0 there, and I'm going to put a 0 plus 0i. So I have all the coefficients there written out. And then I put a plus 0i on the ends of each of those. So it's easy to line up. So bring down your first term, multiply by what's in the box. Add them together, so 0 plus 3, there's 3. 0i plus 2i, there's 2i. You're going to have to now go ahead and multiply. So 3 plus 2i times 3 plus 2i. Multiplying that, we get 9 plus 6i plus 6i plus 4i squared. So we get 9 plus 12i minus 4 and 5 plus 12i. So now we can add them together. We get 10 plus 12i multiply by what's in the box. Go ahead and take 10 and distribute it through. So combine our like terms there. Remembering that I squared there is a -1, so -1 times 24 there is a -24. So combining 30 minus 24 there, we get 6. So I'm going to go back up here and just double check my math. 10 times 3, there's 30. 10 times 2i, there's 20i. 12i times 3, there is a 36i. And 2i times 2i, there is 4i. Here, we'll fix that. So we got 30 plus 20i. And so you get 30 plus 56i minus 24. So you get 6 plus 56i. There we have it. So answering the question there, f of 3 plus 2i is equal to 6 plus 56i. No, that's going to go back up there. Sorry. Lost my train of thought here. I'm going to put that back up here. Now we're supposed to add that together. So -5 plus 56i. That is our solution. So again, if I have a monomial there, I like to use direct substitution and substitute it directly in there. So doing so there, I'd have to do 3i to the 5th. Minus 4 times 3i. So you can either write it out 3i times 3i times 3i times 3i. I think that was 5 times. Or I can go ahead and, since it's a monomial in there, you could take everything in there to the 5th power. So 3 to the 5th there is 243. And so now I'm going to, I to the 5th there, I got to write that in terms of I to the seconds. So I can rewrite that 243. I to the 4th there is the same thing as I to the 2nd to the 2nd, or you could write down I to the 2nd times I to the 2nd there for I to the 4th. Just as you've got an even power here, so I've got an I to the 4th. If I had an I to the 6th, for instance, I'd write that as I to the 2nd to the 3rd, because 2 times 3 there is 6. If I had an I to the 8th, I'd write that as I to the 2nd to the 4th, because 2 times 4 there is 8. And then I can always just plug in a -1 there for I to the 2nd and take it to the 4th power. Or again, you could write out I to the 2nd times I to the 2nd times I to the 2nd times I to the 2nd. So this becomes 243 times -1 to the 2nd power. So -1 to the 2nd power, there is 1 times 243 is 243i minus 12i. And so those are like terms, and so when you combine those, we get 231i. All right, so this one here, we're supposed to solve for x. So sometimes we can have complex coefficients for and what's in front of our x terms there. And so if a polynomial equation has complex coefficients there, we can solve for x. So we can set that polynomial equals to 0, which it already is, and we can solve for x. So you want to get that x all by itself. It's really, you don't solve it very much different there from 5x plus 1 equals 0. Don't get intimidated by that I there, that I being in there. You need to get your x term by itself, so get rid of the 1. It was adding, so we have to do the inverse operation, which is subtract. Now we have to get rid of the 5i, so the 5i is attached to the x by multiplication, so we're going to have to divide both sides. So we end up there getting x equals -1 over 5i. The thing here with i's is that we do not leave them down in the denominator, so we're going to have to multiply the numerator and denominator by I. So when we do so, down here in the denominator, we're going to get a 5i squared. I squared has a value of a -1. So -1 times 5 down there is a -5. Now I've got a negative divided by a negative there, which is a positive. And then some people like to write this as 1/5 I, or I over 5. It doesn't really matter. So either one of those works. All right, this next one here is a quadratic. So what are we going to use to solve this? Since we can't factor that, what could we use? The quadratic formula. So A is 3, B is a -I, and C is 1. Plug it into the quadratic formula. You know this. You got this. So opposite of B there is I, plus or minus the square root of B squared minus 4 times A times C all over 2 times A. -I squared there, the negative and the I there being squared is just going to give you a positive I squared, and this I squared there has a value of a -1, so I'm going to put down I squared for now. And then 4 times 3 times 1 over there is going to give us a 12. I squared has a value of a -1. So we're not going to leave that as a square root of -13. Remember, that's the same thing as square root of -1 times the square root of 13. So a square root of -1 there is I. And so since both the terms up there in the numerator are the same there, we could just pull that GCF out. And if I pull the GCF out there in the numerator, so you can just take it times I, or you could leave it like that. It doesn't matter. You can leave it as I plus or minus I square root of 13 all over 6. Just because both those terms had an I in common, I just put it out last. All right, this is another quadratic here. So what are we going to use to solve for this one? Yes, the quadratic formula. A here is I, B is -2, and C is -1. Plug them into the quadratic formula. This is good practice. Opposite of B plus or minus the square root of b squared minus 4 times a times c. All over 2 times a. So that becomes So it becomes 4 plus 4i all over 2i. So I'm looking inside the square root there and seeing that both those terms underneath the square root there have a 4 in common. So if I take the g sub of 4 out of that, I get 1 plus I. Because if I take a 4 out of 4 there, I'm left with 1. If I take a 4 out of 4i there, I'm left with I. So, and then the whole thing is still over 2i. So now I can actually find the square root of that 4 inside the square root there. Check your numbers on the outside. Are they divisible by anything? Yeah, those numbers there are divisible by 2, so we could reduce this whole thing down by 2. So now we're going to end up here with 1 plus or minus the square root of 1 plus I all over I. But we can't leave an I down in the denominator. So I'm going to multiply the numerator and denominator by I. So down there in the denominator down there, that's going to be a negative 1 eventually. And so we might as well just, negative up or a negative down doesn't really matter there, so let's just bring it up. So I just brought the negative, divided by a negative 1 is the same thing as multiplying by a negative I there. So since you've got the negative, the I was here, I divided by negative 1 there is just a negative I. So that's why now I just put it out in front. And then I left that 1 plus or minus the square root of 1 plus I in the parentheses. Quadratic formula, shouldn't be too bad. All right, I can evaluate polynomial functions at a complex number. I can solve a polynomial equation with complex coefficients.